Welcome to an episode of Rudy's Electronics Lab. And I think 2 episodes ago I introduced my new Agilent counter here and was looking a little bit into how we could actually see like not only the 12-digit display that's up here, but also the 13, the 14 and the 15 digit that we can actually get on a computer screen from here. And since then, after publishing this video, I had a lot of interesting discussions also in the EEV blog about this instrument, about its particularities. Also learned a bit about its interval technology that actually allow us to measure a bit more precisely than you would normally get given the number of pulses that you can observe within a gate window. So learned a lot of interesting stuff, but there's still a lot of stuff I'm still kind of figuring out, including these flashing lights over here. I'll do another episode on that, but also the question of accuracy. How reliable can we actually measure something and how useful are these additional digits here? And again, I'm interested in comparing, for example, clock sources. So not so much in the absolute accuracy of the crystal in here, but comparing a couple of sources. Now, one of the people in the EEV blog made an interesting comment. He basically said the proof of the pudding is basically when you would have a signal source that you would allow to make very small incremental steps and eventually see the least significant digit going up one by one, just as a basis of the signal that you're sending in there. That will be the ultimate confirmation that actually you will be able to do a reliable type of measurement. So I thought I would set myself to this task. Can we somehow measure the 13 digit, 14 digit, or maybe even 15th digit of the device in that way? Now, I took out some signal generators here to create a signal that I will be measuring. But a little bit to my surprise, actually, I don't have any instrument that can actually take small enough increment steps to do this. So for example, here we have the Rode and Schwartz SMIQ, and that machine actually allows us to make increment steps of 0.1 Hertz. That is the smallest increment step that I can make on this device. Now, how many digits are these? Well, that depends, of course, also on the most significant digit. We need to know both the most and the least significant digit. So this device can go up to 3 gigahertz. The smallest incremental step it can make is 0.1 hertz. So as a result, we would have 11 digits that we have control over. So that's not enough. That's even less than is on the display itself. Then we got the Anritsu here. So what can the Anritsu do? It can basically do 0.01 steps in frequency. It can also go upwards from 1 gigahertz to 3 gigahertz. So that would actually give us 12 digits of resolution. I also checked my Rode and Schwartz CMU 2000. Can do only 11 digits. A Agilent counter that I was having. It can do 0.01 hertz steps, but it cannot go above 120 megahertz, still only got 13 digits. So I was a little bit lost how to create the right signal. But then after that, the solution presented itself to me. Because I was going to use a GPS disciplined oscillator, the Leo Bodnar that I've been talking about in some of the recent episodes here as an external reference source here for the measurement. But actually that device has a second output that is programmable all the way up to 1.4 gigahertz. So I was looking at the smallest steps that you can make with that particular device. And initially I was a little bit set up because I tried to create small steps and the software always crashed. It turned out that you have to do that right, put in not a comma but a period, otherwise it will crash. But actually we can do here 0.001 hertz of incremental steps. And since we can go above 1 gigahertz, that basically means that we have up to 13 digits that we can manipulate here. We don't have all the way up to 14 or 15, but at least 13 digits that can do that. So let's go and do some experiment and how we can be doing that. So how does the experiment go? I set up my meter. It's externally clocked to the Bodnar GPS DO for its sync, and the second channel is coming here, and I put it at 1.2 gigahertz, slightly above 1.2 gigahertz. Why did I choose that particular value? Well, first of all, you want it to be above 1 gigahertz because otherwise I cannot get my full 13 digit of manipulation. I will be using then the third channel input here, which is equipped right now with a 3 gigahertz prescaler. I won't be able to do any channel preconditioning, but that's the way it is. It turned out to be not really a serious problem. I'll be setting machine to a given number of digits here on the display. Now we have a bit of a discussion, you know, how this mode compares to setting the gate time and the other modes. I think we're not fully there, but I think we can safely assume that this is the most accurate mode that the device had, but it's also the mode that by far takes most time for a measurement. So the measurements I've been showing you today are going to take like a couple of minutes, up to 60 minutes, and some of the measurements actually going to take like more than an hour and 10 minutes or so. So that's what we're doing, and we'll be manually starting the device here. So right now it is set on only showing 11 digits, and I'm opening the gate, and this is going to take us some 8 seconds or so, and we should be seeing it measuring 1.2 gigahertz, and then also on the external monitor we get to see 1.2 gigahertz, both at 11 digit resolution. But now we have the ability to increase that resolution, and anything above 12 digits will actually be shown here on the screen, rather than on the device itself, which is limited to 12. So the big exercise now is going to be, can we do incremental small steps and really see how the device is behaving? Now, because all of these measurements take quite a lot of time, I made screen prints, so I'm not wasting hours here. So first I'm sending out 1.2 gigahertz plus 0.011 hertz. And let's see if the meter can actually measure that properly, and yes, there we go. He's showing 0.11 hertz on the right hand side of the screen with the serial interface coming from the Agilent. And just to check how many digits we got, yeah, it is 13 digits, so 1 digit more than the machine itself can show us. Now we're going to increase this by 1 increment step, so 0.012, and he measures that correctly. 13, 14, 15, and I'm going on here, and as we will see here, basically all the different steps are properly being picked up as a measurement, and I'm actually going all the way here, I think, to 0.022, and I'm very happy because we basically see that each of the measurements is properly executed here. Now I cannot make the Leo Botnar making even smaller steps than this one to get to the 14 and 15 digit, but I have been enabling that measurement for it. So now I'm basically going to run the extra digit for 14 bit, and what I get, I send out 0.023 and I get 0.0230. Yeah, so that's exactly what I would have wanted to see. And let's add one more digit, and actually this is going to be a measurement of over 1 hour, and then I'm basically getting 0.00. So that looks very, very good. Okay, that's it for now. Well, I think it's kind of cool because we can establish that actually using this methodology, we can actually manipulate each of the digit and do a reliable measurement over it. So it seems that this instrument is accurate enough basically to make up to 14 and 15 bit type of measurement. Mind again that this is a relative measurement to the time source. If you want to make an absolute measurement, then everything will depend, of course, on the accuracy of that absolute time base. And the built-in time base, as many people have noted, the standard version is very, very poor. I will actually be upgrading that to another version, and I also got like a Morion 89 crystal coming in a couple of days. That's even a couple of steps above yet, but we're always going to be dependent basically of our time source. But as long as we're making relative measurements, we can go really far if we're patient enough, but the instrument is able to do it. I hope this was a useful episode to you. If so, please do subscribe to the channel and watch a couple of other videos that I did on the Agilent, on the Leo Botnar, actually all the other devices that you're seeing here, and see you next time.